So let's talk about the residue term, which is a very useful term for computing integrals, and not just path integrals, but it's basically, the idea is to use what we know about isolated singularities and use what we know about the Lorentz series and different ways of computing the coefficients, especially one of the coefficients, to make it very easy to give us a sort of calculus for computing these intervals, right? So the basic idea is that if we have a function f with an isolated singularity, so maybe it's defined in some just like this, right? If we expand it around this point in a Lorentz series, right? Then all of these terms that except for -1, when n is -1, all of those guys, if I integrate around the loop around t, I'll just get 0, because all of those terms except for n equals -1 do have an antiderivative in this actually in the punctured plane. So really, if I take an integral around the loop, it really only sees the negative, the coefficients of when n is -1, right? So we give this a name, and say it's the residue, we'll shorten this RES, of f at t, and say this is the c -1, right? And you can sort of think about it. Well, it's the residue. If I integrate around the loop, it's the only thing that's left, right? So that's why we call it a residue, right? Now, that's a nice definition. So what is it, right? Well, it is, we have a formula for these coefficients. So in terms of an integral, it's basically I can compute it, at least, in terms of some integral around some circle, where S should be, of course, there's an R over there, right, of F of, why am I putting this so far up? This guy, right? Okay? So if I, this is basically the thing that we want to compute, right? I mean, this goes both ways, right? I can compute this coefficient using this integral, or I can use this coefficient to compute this integral, right? So it goes both ways. And actually, the way that it's going to be mostly used is that you compute this residue somehow, and to compute these kind of integrals. Now, if it was just these kind of integrals around loops, then it wouldn't be very useful. But we do have all this quotient theory to generalize this to basically, where did I put that? To basically any cycle that goes around some singularities, and that is the residue term. So suppose that I have an open set. I have finite set in this U. I have an F, which is going to have isolated singularities on this finite set. So holomorphic function defined outside of S. Let's suppose that I have gamma, a cycle gamma in, so this guy shouldn't go through S, so it's going to be in U S, but it's homologous to 0 in U. So it can go around points of S, but it's not supposed to go around any point in the complement of U, right? The binding number of gamma around any point in the complement of U is 0, right? Then we can compute the integral, right? This is just you have to put this 2 pi I somewhere. Gamma f of z dz is equal to sum over all the points in S. So it's just a finite sum. We look at the winding number around P gamma and multiplied by the residue of F at P. Right? So, and the way this is usually used is that you can somehow figure out how to compute this side to compute this side, right? So, and these things, well, these things are usually, in a lot of the applications, you sort of get to pick gamma in a certain sense. I mean, to a certain degree. Usually, you pick these to be 1, or pick gamma so that these are 1, and then you just have to compute the residues, right? And there's a variety of ways to compute the residues. Let's prove this term first before we look at some applications. So, and it's it's basically, I mean, we know that this thing is sort of an integral like this, except this is gamma is not gamma, but it's a little circle around P, right? So we just have to, basically that's the idea, to reduce it to to little circles around P, right? Unfortunately, I have to won't have enough room to prove, so you should memorize this right now. You can, in the video, you can always go back, right? So, let's let's give the points an S name, right? Let's call them W1 through WL. I think I did it in my notes. And now we're going to pick small disks, delta R1, and I'm going to make them closed disks, RL, WL. These should all be in U, right? And they should be, maybe I can keep that side of the board or something else, mutually disjoint. Right? That, if I take any two of them, they do not intersect. And clearly I can, for a small enough, use open, right? So if I have some finite number of points, I can, around each one, I can pick a small enough neighborhood, small enough closed disk, such that none of these closed disks intersect and they're all inside you, right? And those are our little, little circle. Well, right now we're taking disks, but we're taking their boundaries are those are our little circles. So let's define a new cycle. Lambda is going to be gamma, our cycle that we're interested in. And now we're going to subtract. I'm going to take the winding number of gamma around W1, and then I'm going to take that many copies of this circle. Right? Oh, well, the boundary over here, right? The circle of radius R1. And I do this, and I subtract this for all of them, right? So finally, WL, and the boundary of the Lth circle, right? Now, I claim that this lambda is homologous to 0 in U minus S. Remember, gamma is homologous to 0 in U, right? So if P is not in U, right? Then if I look at the winding number of gamma around P, right? In all of these, if I take the winding number over this cycle, right? These are just integers, right? It's really the winding number around of this around P minus this, this many times the winding number of this around P, and so on, right? So we always have, for any P, we always have the winding number of gamma around P minus first the winding number of gamma around W1, that is the winding number of this circle around T minus minus L, just the same thing. Let me write it out here. Gamma WL, the winding number, I'm going to run out of room, or L, WL, T, just barely made it. Okay? Well, so that's what it is. This is like, for all P, except the ones that, of course, wouldn't lie on any of these curves. But so the idea is this, right? Maybe let me use this room to sort of make a picture. Maybe this is gamma, right? Maybe this U is some big thing, and S is going to be these points, right? We pick small circles around each, right? They're all, all of these guys are, basically by definition, they're the positively oriented, going around once around each one of these, circles, right? And so what this is going to be, if this was, let's say, W1, W2, W3, and there would be 3 terms over here, right? We have gamma minus, the gamma goes once around W1, so 1 times this guy, right? the winding number, I'm talking about what gamma is. Then around this circle, this, again, we would take once this guy, and we take 0 times this guy, because gamma does not wind around W3. And then the winding number on gamma, well, it's first, well, basically I want to show that it's 0 as long as P is either not in U or P is in S, right? So if where's my eraser? So if this is going to be always true, so if P is not in U, then we have and this is 0, well, that's because gamma was homologous to 0 in U, right? That's what that meant. And we also have, these are all, the way that we chose these was to be a subset of U, right? So, the winding number around anything in the interior, the winding number would only be non-zero, for points in the interior of these disks, right? And those are all in U, right? So that means that all of these winding numbers is also 0, right? So we have N R K W K P is 0, right? So this is for all K. So we have that the winding number around lambda around P is 0. Okay? Now if P is in S, right? Then, well, the winding number of gamma around P is, well, whatever the winding number of gamma around P is, right? We don't quite know, right? But it's basically, this is when P is equal to, let me call it it's WK, right? So let's say the kth one, right? But in that case, we get that the RK WK is because, well, this is P, so this is 1, right? And it's 0 RJ, let's say. J is 0 if J is not equal to K, right? What does that mean? We look at this formula, right? And, well, it's the winding number is whatever it is. And then only one of these terms survives. It's going to be the kth one, right? The kth one is going to look just like this, except with a K over here, right? And this is going to be 1. And this is going to be precisely the winding number of gamma around P. So that means that this 0, winding number of lambda around P is also 0. Okay, so now we have, what do we have? We have that lambda is homologous to 0 in U minus S. All right, keep the picture up. So lambda homologous to 0 in U minus S, right? Okay, well, that means that we have Cauchy's theorem, and Cauchy's theorem says that let me put the 1 over 2 pi I here around lambda, that this is going to be 0, right? So this is Cauchy, right? We're using the homology version of Cauchy. All right, well, what is this? This is, let me write that over here, this is equal to, well, 1 over 2 pi I. Let me just put that out front. Integral over gamma minus n R1 sorry, gamma W1, the integral over R1 W1 let me make my work simpler here. Let's use this. Or maybe since we've already named them J of 1 to how many of we have? L, I think, right? So this is n of gamma Wj, the integral of over this circle of Rj Wj f of z dz, right? Okay, well, this is equal to, let me maybe distribute the 1 over 2 pi I, 1 over 2 pi I, gamma. We're betting it up, right? Minus now, what is this divided by 1 over 2 pi I? Well, that's precisely the formula for the residue, right? For the minus first coefficient of the Laurent series around Wj, right? It's precisely the residue of f around Wj. Right. Well, that's it, right? I mean, that's the proof. Okay. Now, maybe immediately it's not quite clear what's the how can this be useful, right? Because it just relates one integral to another integral, or maybe a bunch of integrals, right? But that's the point is that there's actually nice ways to compute the residue. Right? We've seen that we can compute Laurent series, and by some tricks. If we have sort of a formula maybe for f, and if we're not even interested in the whole Laurent series, we're only interested in the residue, in the minus first coefficient, then there are easier ways to compute it, especially if those singularities are not too bad. The nicest thing is if there are poles. Right? If they are removable singularities, then and the residue is 0. Right? So we're fine with removable singularities. We don't have to worry about them. Essential singularities are a little bit harder. You have to work a little harder to compute to compute the residues, but for poles, they're easy, and poles come up quite often. So, in application. So let's so let me just give you a couple of ways to compute the residue, and their proofs are really simple. Maybe the first one I'll prove, and I'll leave the next two as exercises, and they're not hard exercises. So the first one might seem stupid, but let me name all of them propositions. So suppose F is holomorphic in this neighborhood, in this disk. G is holomorphic in, so G has an isolated singularity. Right? And the residue of F plus G around G is just the residue of G. If you think about it, it's actually not hard to prove at all. So if we have if we take a little disk, something smaller than R, and I compute the residue. This is proof already, right? This is going to be the residue. So S is something smaller than R, right? That's the residue. So it's maybe it's almost too much to write down, right? It's sort of obvious what is happening, right? F is actually holomorphic in the entire disk, or well, that's the real singularity at P if you want to. You want to have both of them to have a singularity. That means that this integral is 0. Right? So therefore, the residue of F plus G is equal to the residue of G. Okay. Let me raise this thing just so that I can get all of these techniques on one board. So suppose F is holomorphic, so it has a singularity at P, right? Then if P is a simple pole, then the residue of F at P is the limit as Z goes to P of Z minus P F of Z. Right? It's precisely the thing that was a simple pole. This thing is supposed to have a removable singularity, right? And so it's basically, once you remove that singularity, what is the value of that function, right? This limit exists because it's a simple pole, right? And we're asking what it is. Now, if P has a pole of order order k, then there's a way to generalize this. And residue of f at p means that it's a little bit more complicated. So 1 over k minus 1 factorial. Then I have the k minus 1 of derivative. Oh, yeah. And I forgot to put in the limit. I'm forgetting something. Limit z goes to p of the k minus 1 derivative of, and we know that this guy is supposed to be have a removable singularity, right? That's the smallest k, right? Because that's the order. It's the smallest k, so it is a removable singularity. So that's a holomorphic function. So I know this limit exists, right? I mean, I could extend this function through the singularity and then just evaluate it at p, right? Well, evaluate its k minus 1's derivative, right? And that's really the same formula as this thing. If k is 1, right? No derivative. K is 1. This is just 1. All right. So the proof of this is left as an exercise. Basically, just you write down the Laurent series. Right? Write down the Laurent series. Figure out what that function is, and it sort of automatically pops out. Proposition. There's another one. This one's actually quite useful, even though it looks kind of specialized. But it's quite useful because it's often really easy to use if you can use it. And there's tons of others, right? So these are just some to look at maybe the most common ones. Let's suppose that I have see what I named these functions just h and g. I did precisely the opposite in notes, so let me do the same thing as in notes. Suppose that f is this, and g has a simple 0 at p. So meaning this thing will have, and these are h and g holomorphic, right? Holomorphic near p. So this is a meromorphic function. It has a singularity at p. It has a simple pole at p, right? Well, you could actually use this, but then if you actually have this form of it, then this is sort of a version of L'Hopital's rule, actually. Or you could think of it as an application of L'Hopital's rule if you would prove that for homomorphic functions. It's still true. L'Hopital's rule still works for holomorphic functions. But in this class, you have to reprove it if you want to use it. So the thing, again, the proof is not hard. Well, proof of what? The residue of f at p as well, it's divided by g prime at p, right? So if you have these formulas, right, very simple formulas, that you can evaluate them, evaluate the derivative, then it's really easy to compute the residue. And again, left is an exercise, but not hard. Okay, so that means that we can actually compute the residue quite easy without really trying to compute some integral. All right. So let's look at let's look at an application of residue theorem, sort of a typical application. Although it was going to be, we're going to do a very simple function. So where, a very simple integral where you can actually compute it using sort of more classical calculus. There's lots of different integrals where the residue theorem is actually sort of the only or the easiest way of doing it. But the reason why I'm going to do something simple is, well, to make the computation simple. Sort of, this is in some sense almost the simplest example of something that's doable by residue theorem. Fairly typical application. So suppose that I'm trying to evaluate that's right. Let's suppose that we don't quite know the antiderivative here, right? We're not going to actually use the tangent. But how do we do this using the residue theorem? Well, so the way that we do this is we're gonna write this, and this is maybe this requires a little bit of justification that this is true, right? I mean, normally is two limits, right? Why can I write it as one limit? I can. I'll leave it as an exercise. Why is one limit enough? Why is the symmetric limit enough? Good exercise. The exercise is just to come up with it's a 3-word answer if you put in the subject, verb, and object. All right. So if we look at the interval from minus r to r, we're definitely looking at an integral from minus r to r, right? So we're looking at this path integral. That's really what this is. This is the path integral from minus r to r along this segment, integrating this function. But now what we're going to do is we're going to come back using a semicircular path gamma, and go with gamma sub r. Gamma sub r of t is going to be e to the r e to the it, right? And t is going to go from 0 to pi, right? So I'm going all the way around the circle, it's going half circle, right? And we're gonna, let me leave myself a little bit of room. We're gonna let gamma sub r be this interval minus r to r, and then we're gonna, this is chain addition, right? Use gamma r. This is a cycle. You can check. Now, the function that we're looking at is 1 over 1 plus z squared. And actually, we get that the integral over this gamma r 1 over 1 plus z squared dz. What is this integral? Minus r to r dx, right? Right, it just follows just by parametrizing this thing by x. And plus gamma r 1 over 1 plus z going to be a couple of things. We want to compute this thing. We don't know what this is. And actually, we won't know what this is for any specific r. We're just going to actually take the limit. Right? We're going to compute this thing precisely. This is a cycle. And we're going to not quite compute this thing. We're going to bound it. So so it's not going to be bigger than something. Now, this function, it has two poles. Right? I can factor this thing. Let me write it. Z plus I, Z minus I. Go right like this. It has two poles. It has a pole at I and minus I. Minus I. Minus 1, minus I. Alright? Now, we have a cycle, right? It's going around, our domain, our U in the residue term is just all of C, right? So this our domain is C. The finite set of points is this and this, right? And this gamma sub r goes around I once and goes around minus I 0 times. Let you double check that it really does that. That the winding number is around this thing is 1, around that thing is 0. Okay. So, so we really need to figure out what are the residues, right? So what is and we really only need to figure out the residue around I, right? So residue of 1 plus z squared around I, right? And now there's a bunch of ways to do this. One of the ways, I have to double check the computation here, is you could use partial fractions, right? That you know from this was the one with plus. This is a 2. Z plus I minus I over 2. Z minus I. Z plus I. I said I and I wrote 1. Okay. Right, and this partial fraction. Now, at I, this guy is holomorphic. So the residue is the same as the residue over here, okay, of this guy. And the residue of this guy, I mean, that you can just see it, right? It's minus I over 2. Okay? And you could use some of the other versions of the residue term, of these propositions to compute residues. You could, for example, if I multiply by, it's a simple pole, right? So I can multiply by z minus I, and I just get 1 over z plus I, and I'm evaluating that at I, so it's 1 over 2I, right? Which is the same thing as minus I over 2, right? That's the same thing as 1 over 2I, right? Same number. Okay, so that means that we have, maybe if I erase something, let's, what should I erase? Let's erase the picture. We've seen the picture enough, so maybe let me erase this for a moment. And so we have R of 1 over 1 plus z squared dz. We know that this is, well, it's the if that would be 1 over 2 pi I, it's really 2 pi I over here, times the residue of 1 plus c squared around I, right? And this is, well, I can use maybe this form, 1 over 2 I, right? And so this is pi, okay? By residue term, okay? Now that doesn't quite tell us everything yet, right? That just tells us what this thing is, right? And we want this, we don't yet know what that thing is, right? It's not 0, right? But we're not even interested in this thing exactly. We're interested in what's happening as this, as r goes to infinity, right? Okay, so now we've used the residue term, so I can erase that. So if we can show that this thing goes to 0 as r goes to infinity, then we're good. And that's what we're going to do. Right, this thing, and let's let me just write down what it is, right? 0 to pi of, remember gamma sub r t is r times e to the it, right? So I'm going to get 1 over 1 plus this z squared, right? That's gamma sub r e to the I to t, right? And then I will have, well, the dz, right? So it's r I e to the I t dt, right? So far so good, right? I don't want to make any mistakes here. So now we've not equal to, let's do less than or equal to. Keep writing equal to. Less than or equal to. We take everything inside, right? And we bound the, let me see, make sure that I'm, yeah. We bound, this is going to give us pi, right? If I take the absolute values inside. Well, let me maybe write that down, just so that it's what we're bounding is really. So maybe even write it even more. 1 plus r squared e to the tt. This and then. If I take absolute value or modulus over here, I'm just going to get r dt, right? So and r is some constant, right? So this r is going to give us, I'm going to again bound it by basically the maximum of this value of this function inside times length of this integral, which is pi. So it's pi times this r is r. This thing, well, we have to if we're bounding 1 over something from above, we're bounding this thing from below. And so we're trying to get we're gonna get and this is, remember, R is big, right? So you don't have to worry about this vanishing. R is very, very big, definitely bigger than 1, right? So if I, what's the smallest this can be, right? This goes around a circle of radius r squared, set it at 1, and we're looking at what's the minimum distance from 1, right? And it's just r squared minus 1, right? In any case, this goes to 0 as r goes to infinity, right? So this goes to 0, this is pi, and therefore this limit is pi, right? So this 0 as r goes to infinity, right? And this thing is pi, and that integral. All right, let's look at one more application. This is maybe I'll leave more of the details out, but another application of residue theorem that's quite common is to really just recognize that recognize a path integral, right? So, for example, suppose that we have this thing. Let's see be some positive constant bigger than 1, right? And suppose that we're interested in this integral, right? And a priori it doesn't look like a path integral, right? An integral around a cycle, right? But if you notice something, that on the unit disk, z bar is 1 over z, used a bunch of times, and cosine theta, right? Well, that's the real part of e to the I theta, right? So if this is z, if z is e to the I theta, and this is, well, this is z plus z bar over 2. This is z plus 1 over z over 2, right? All right, so this looks like integral around z of 1 over c plus z plus 1 over z divided by 2. Now I have to figure out what d theta is. Well, if I had dz, right, then dz would have, if I'm going around the circle, right, it would have I e to the I theta in front of it, right? So I have to get rid of it. So it's going to be 1 over I z dz. If you work out what this path integral is, it's exactly this integral, right? Okay, and now we can use residue theorem. Let me, so that I don't mess up the algebra. I'll just do what I did before, and I'll just give you what it is. Plus 2c z plus 1 dz, right? And now you figure out this function has 2 poles, right? Has poles at it has poles at minus c plus minus square root of c squared minus 1. One of them outside unit circle, one of them inside unit circle. And remember, c squared is a number bigger than 1, right? So we're getting this thing. It's on the real line, right? So you get that this as star, well, it's going around the unit circle, so we get that star is equal to, well, it's this minus 2i. It came out of the algebra times 2 pi I, because we didn't have a 2 pi I in front of this, times the residue of 1 over z squared plus 2 cz plus 1. And the one that's inside the unit circle, and that's the one with the plus sign. So minus c plus. I'm leaving some of these details for you to check. To figure out where these guys are. Figure out one of them is inside the unit circle, one of them is outside. And all right, so we have this. And if you compute all of that, I'll let you compute it using one of these techniques. Again, it's a simple pole, right? So it's it's all about computing one of those limits or using this derivative thing, right? However you want to compute it. It's fairly easy to compute. It's just a bit of messy algebra, but it comes out to 2 pi over square root of c squared minus 1, right? And it's okay. If I did all the details, it would take up a little bit more, but it's actually not a bad computation, right? So if I have something that sort of looks like, this sort of remind you of something that might come from a path integral around the circle, right? And especially if you have sines and cosines in there, yeah, I mean those things might count. And then you just have to sort of play some tricks like this to write everything in terms of something which is holomorphic except maybe some poles, right? And then you just compute the residues at the poles that you've introduced. All right, now so that's basically the sort of the classical applications, right? Or applications of the residue theorem as a theorem, and really so for example the undergraduate complex analysis class is usually you set up stuff until you get to residue theorem, and then you spend a couple of weeks computing a whole bunch of integrals. And there's a whole bunch of different techniques, a whole bunch of different integrals that you can compute using the residue theorem. These are only two sort of samples. It's usually either recognizing something as a path integral, or it is writing something, writing some integral. A lot of times it is this integral over some infinite or half-infinite interval. Writing it as a part of some path integral, and then somehow bounding or getting a handle on the sort of the return trip, right? Sometimes the return trip sort of goes around a big circle. Sometimes it goes back, sort of maybe just just shift it up. It's sometimes you have to go around some singularities. There's all sorts of stuff that comes up, but it's and there's no for a single integral there's no it's not going to be just always just one way of doing it anyway, right? So all right, so this was really just a sample of what can be done, and we'll actually use for us the residue term is going to be more about how do we use it in the other stuff that we're going to do, right? Not necessarily just for computing integrals, right? It's just a fun application. It's just when it comes up in applied. It's the simplest way where it comes up in applied math, right? And it's maybe one last thing is it's kind of an interesting place where this comes up, right? It's even looking at this, right? Over here, if you were just coming out of calculus, there's no complex numbers in there. It's not an integral over something in the complex plane. right? And there's it's a lot of these things is recognizing when is that function that you're integrating, when is it actually, the restriction to the right path, right, of some holomorphic function, right? That's really what we're doing, over here, right? So, okay, so, right, so that's the residue term. We'll get to counting zeros and poles next.